Okay, so we are now ready to develop the occupation number representation. And what I'm going to do is I'm going to develop this by giving you some examples, and then we'll infer the general rule from the example. So I'm going to start off, and I'm going to draw two columns. This is the old non-relativistic quantum mechanics language. And then over here, we will have the new occupation number language. And I just want to give you a list of states using both descriptions. So let's just start off with perhaps the simplest state that we could think of. This is just our single particle state of momentum K1. So instead of describing this as a state in Fock space, I'm going to describe this using a function. It's going to be a function of three variables, n of k, so a function of kx, ky, kz. And for this particular state, n of k is just a delta function, delta of k, comma, k1. And nicely, because we're in the box, this is just a normal delta function. Okay, now let's look at a two-particle state. So perhaps our first particle has a momentum k2, k1 at least, our second a momentum k2. The occupation number function that would correspond to that, even though I've got two particles, it's still just a single function of three variables. And it looks like delta of k, k1, plus delta of k, k2. Two delta functions because there are two particles. Okay, one more, and then I think we've made the pattern clear and we can start to test ourselves a little bit. Let's imagine we've got a three-particle state with momenta K1, K2, and K3. The occupation number is still a single function. There's a delta function for K1. There's a delta function for K2. And there's a delta function for K3. And these are all just summed. Okay? Now, of course, one entry that is missing from this list, I could have the state with no particles, the vacuum, and this just corresponds to an occupation number which is equal to 0. Okay, let's just fill in some lines so that the table is absolutely clear. Now, look at what a big advantage this language is. Previously, if we were talking about two particles, we had a function of 6 variables. If we talked about three particles, we had a function of 9 variables. So the way that we would describe the different states in the different n particle Hilbert spaces changed a lot. Here, whether I've got no particles, 2 particles, 3 particles, whatever, I always describe the state using a single function, the occupation number function, for the state, no matter how many particles I have. How does the number of particles enter? Well, each particle in the state gets its own delta function. Okay? And now it's a nice Kronecker delta, not a direct delta because we're working in the box, but each particle in the state gets a delta function. If we had, say, maybe this is a nice one, let's take K1, 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 so all three particles are in states K1. Well, look at the example just above, okay? We would have delta K, K1, plus delta K, K1, plus delta K, K1. So this would land up giving us just 3 delta K, K1. So if you look at the delta functions that appear, that tells you the momentum states that are occupied, and the coefficient of the delta function tells you how many particles are in that state. Okay, I'm going to write down an occupation number state. So here it is. I'm going to say I've got 2 delta K, K1, plus I've got 3 delta K, K2, plus I've got delta K, K3. Why don't you have an attempt at writing down what is the ket in Fock space that corresponds to this occupation number function? Pause the video, write it down, and then unpause the video. Okay, you got an answer? Great. So let's see. This is my answer. So 2K1. So I'll have K1, K1, 3K2. So I'll have K2, 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 and then K3. So this is K3. So this is a 1, 2, plus 3 is 5, plus 1 is a 6 particle state. 2 of the particles have momentum K1, 3 have momentum K2, 1 has momentum K3. But what should be clear to you now is that there's an absolutely transparent way to translate any state in the Fock space basis into an occupation number function, and any occupation number function can be translated into a Fock space state. So these are 2 completely equivalent ways of discussing the physics. The great thing about the occupation number language is that it doesn't matter how many particles you've got, you always describe the occupation number function as a single function of 3 variables. So we've got a lovely, simple description. Remember how ugly our wave function on Fock space was. Look at how beautiful our occupation number representation of Fock space is.